Hi, everybody, and welcome back to the spring semester of the Foundation Seminar. So it's my pleasure to introduce Uri Kol, who is joining us from the CMSA, and is going to be talking about quantum criticality in black hole dynamics.
Thank you very much. And thank you everyone for coming. I wanted to share some recent results with you. For two reasons. One, I wanted to share and see the feedback, but also I think it's a subject that is appropriate for the Foundation seminar. And in this spirit, let me start by posing this following question. Do we have robust predictions for black holes? And that's kind of the motivated question for this research. But before I give my own answers, I wanted to see what people think. Are people satisfied with the current theoretical situation in black hole physics?
Classical or
whatever. In the predictions we have for black holes, that given the enormous experimental progress, are people happy with the current theoretical status? Do you think that our predictions are good enough or not? What do people think?
I think classical black hole models are doing well.
Doing well is not robust predictions.
Well, they were predicted and now they are being observed. They're doing okay.
Okay, and the other opinions, or do people share the same opinion?
In the future, there are more like gravitational, more accurate, or more precise
exactly.
gravitational waveforms.
Right,
I mean,
right.
data coming, we might need better model.
Right. So the motivation for this question is indeed experimental, and in this building I don't need to say too much about black hole experiments, but let me just briefly mention we really have plenty of opportunities these days involving black holes in different types of experiments. One of them is through gravitational waves. So this is a catalog of the LIGO-Virgo-Kagra collaboration that measure gravitational waves from binary mergers. Most of them are binary mergers of black holes. So there are about 100 events detected so far, and there are going to be a lot more, not only by this collaboration, but also by future experiments that are planned for the near and intermediate future. So the future is really promising in this sense, and I think I don't need to say too much about this. For sure, I don't need to say a word about the Event Horizon Telescope and the photon ring. Very promising, and we have good amount of data, and that's only going to improve. So the question is, in the era of precision black hole physics, we have plenty of measurements. We're going to have more measurements, and they're going to be more and more precise, and there is a strong need for robust predictions. By the way, can I move this thing?
I don't know why that's happening.
Okay, maybe we'll just keep it like that. Yeah, so there is a strong need for robust predictions. And let's discuss it a little bit. We'll see what people think. But at the very least, what I want to claim is that, okay, first of all, the term robust prediction, there is no objective definition of what it is. It's a little bit a matter of opinion. So it depends on your standards. But at the very least, I want to claim that the predictions we have for black holes do not meet the standards that for past predictions that we usually have in other areas of physics. And what do I mean by that? So in most areas, or in many cases in physics, when we talk about robust predictions, we have in mind symmetry breaking. So the paradigm of symmetry breaking has been incredibly fruitful and useful in physics in almost all areas of physics. Perhaps the gold standard is in condensed matter, where we can classify different materials and different models into different universality classes. So we can study the phase structure of different materials and different models. At some critical points, there is an unsymmetry, and the symmetry is broken, and the physics is controlled by a set of critical exponents. And in this way, we can associate a material or a model into different universality classes. And that's what we would usually call a robust prediction. So even we can compute different things in the different phases, different quantities, but just computing something or measuring some quantity by itself does not usually count as a robust prediction, because it's sensitive to a lot of to many different things. And of course, the paradigm of symmetry breaking has been useful in other fields. In QFT, in particle physics, it's so common that I will not have time even to list the number of examples. Perhaps the most famous example is the Higgs physics, but needless to say that it's been incredibly useful and fruitful paradigm. And in cosmology, we can also understand cosmic inflation as the breaking of the zeta isometries. Now, in each one of these cases, the mechanism and the physics is different, but the paradigm is similar. The paradigm says that the physics is not symmetric. Some perturbations, some fluctuations break the symmetries. However, the way in which the symmetry is broken constrains, and sometimes severely constrains, the physics. Okay, and this paradigm led to strong predictions in many cases. Okay, and what I want to claim is that we don't have this kind of picture for black holes, and that's what I want to develop here. So
you don't think Kerr is a symmetry breaking version of Schwarzschild?
it depends what you mean by that, but the general answer is no.
Okay.
You have to tell me what you mean by symmetry breaking, and indeed there were efforts. We can discuss examples in the literature, the bottom line, at least in my opinion, they didn't lead to the kind of things that we call robust predictions. In condensed matter language, I would say that what characterizes a robust prediction is a phase which is characterized by critical exponents. Something like that. We don't have something like that for black holes.
Can I?
Yeah.
So not symmetry breaking, but for instance, the simulations of black hole mergers,
Very good.
there's well very strict prediction on
Very
what we
good.
would observe.
So most of the efforts on black holes have been numerical, and numerics is great, and it's very important, incredibly important. But in my opinion, we cannot use it as an excuse not to explore some qualitative features of black hole and come up with robust predictions. So even in the story that I'm going to show you today, numerics will be important, but I also want to extract some qualitative information about the black hole. And numerics alone is not enough to do that. And hopefully it will become more clear. But that's a very good point, of course. Any more questions? Yeah.
Are you claiming that you are going to find some symmetry breaking, or your claim that the symmetry breaking is done?
Wait.
Wait
for an hour.
If I didn't have a claim, I wouldn't have. So yeah, I'm going to show you a symmetry breaking pattern.
Sure.
So that's a question. What about black hole perturbation theories? Can we identify some symmetry breaking pattern for black hole perturbation theory? And before I answer this question, let me just say a few words about why black hole perturbation theory is important to start with. And the reason is that it describes a few important effects in systems that we currently probe. So in a binary system of two black holes, it describes or it controls tidal effects in the in-spiral phase of the merger. So there are more effects in this in-spiral phase, but black hole perturbation theory does not capture all of them. It does capture tidal effects. It also controls the ringdown phase, the decay of the wavefront through quasi-normal modes. So those are two important effects that are captured by black hole perturbation theory. And in the Icona limit, it also controls the photon ring. So this is a theory that we're very much interested in and would like to understand the structure of its solution. How does it look like? So black hole perturbation theory was developed in the 50s for Schwarzschild by Wheeler and Zarelli. 1963, the Kerr metric was discovered, and following the discovery of rotating black holes, there was a huge effort to develop the theory of perturbations around it. And perhaps the most important result is in this context is by Tukolsky in 1973 that discovered a master equation for perturbations of different spins. So this is the Kerr metric. So I took some screenshots from the original paper. This is the Kerr metric, and what Tukolsky found is that the perturbation around Kerr black hole takes a separable form, and it separates essentially into a radial and angular component. Here S is the spin of the perturbation, and it's a remarkable result. I won't have time to discuss it in detail, but let me just highlight a few properties. I already discussed it last year, but it's so remarkable, so let me repeat it. The separation into the radial and angular components is not implied by the isometries of the spacetime, and no one knows why this is the result. What's the reason for the separation? Until today, we don't understand the reason for that. Probably there is some underlying principle that we don't understand. But anyway, it simplifies the problem a lot, and that's the main reason for the importance of this formulation. And yeah, so this is the Tukolsky equation. I'll discuss it in more detail. And
Uri, just a question on the point you made. So are you saying that even in Kerr, there is no known killing tensor that is associated with this separability here? Like for null geodesics, we have this killing Yano. So are you saying that
no, it's the killing Yano. It's a killing Yano, but
here as well?
yeah,
Like,
the killing Yano is related to the separation, but why the killing Yano should have been there in the first place?
Okay.
Yeah. So this is the Tukolsky equation, and the point is that Tukolsky equation is hard to solve. It's an ODE with 4 regular singular points of the Oin type, and there are no closed form solutions. So of course there has been many attempts and many work, not just attempts, of works and successful works to solve it numerically. But as I will show today, numerics alone is not enough. It hasn't led to what I would call robust predictions. I'll show more about that. Okay, so that's what I want to improve, to provide a qualitative understanding of the phase structure of solutions to the Tukolsky equation. Any questions?
So this is the entire solution, not just the spectrum. You want to, is that right? Or
Yeah, what do you mean spectrum of quasi-normal
yeah,
modes?
right.
Well, in some sense, it's equivalent to say what is the spectrum of quasi-normal modes.
Well, the spectrum, like in some limits, you can get it with WKB, for example, right?
Yeah, but that's an
getting
approximation.
Right, but getting the modes is much more harder. So in this, you will getting the modes, the full mode
Yeah,
solution will be a bit harder.
Yeah.
So in this setup, you are saying that you will get both the modes and
Well, I'm not going to discuss quasi-normal modes,
Okay,
but I'm
okay.
going to characterize the phase space of solutions.
I
Which
see.
let's discuss quasi-normal modes. It's a
Okay.
good point, but yeah. Okay, so so as I mentioned before, I want to develop an understanding in light of symmetry breaking patterns for the Tukolsky equation. Now, symmetry breaking usually goes with words like collective phenomena, spontaneous symmetry breaking, and this kind of phrases. And so the starting point will be a collective phenomena, which is already known for a long time in black holes. It's called black hole super radiance. And based on this well-known phenomena, I will build the rest of the talk. So what is black hole super radiance? It turns out that if you scatter a wave from a rotating Kerr black hole, and if the energy, the frequency of the wave is within this range, where here m is the azimuthal quantum number of the perturbation, and omega h is the angular velocity of the horizon, it turns out that in this range, the wave is amplified. Okay, this is called black hole super radiance. It was discussed first by Zeldovich in 1971. Zeldovich discussed the super radiance more generally, not just for black holes. He commented about black holes, but he discussed it more generally. It was slightly later that Starobinsky and Tukolsky made it more precise for the Kerr black hole. And we can think about it as a rotational version of Cherenkov radiation. It's a collective phenomena of spontaneous emission.
What can you say just another bit about why it's the analog of Cherenkov?
Yeah, essentially it's a superluminal type of. If you think about the wave as the medium and the black hole as the emitter, the emitter is moving faster than some velocity of the medium. Yeah, so that's a general intuition. Any more questions?
So how does that connect with your broader theme of?
I will show now. And yeah, so what I'm going to do now is to jump directly into revealing all the main results, and then we'll break it down. And I'm going to describe the phase structure of solutions to the Tukhowsky equation. The phase space is spanned by two parameters in the equation: the angular momentum of the black hole and the frequency of the wave. Those are the two parameters in the equation. In addition to them, there is the Schwarzschild mass in the equation that will just set the overall scale. It will not play an important role in the story. And there are the integers, S, L, and M. But other than these integers and the mass parameters, those are the two parameters in the equation, and they will span the phase space of solutions. Now, I will try these two parameters by the following parameterization. So I will try A, the angular momentum of the black hole by the Hawking radiation. Okay, if people are not familiar, I can show there is a formula relating them, of course. And I will also define this combination, A times omega, I'll call it G. And for now, let me just say that it's a choice that I can make to parameterize the phase space. I can choose combinations. Hopefully, it will become more clear the importance of this combination as go on. But anyone that have looked at the Tukhowsky equation may recognize this combination. Anyone? Did anyone look at the Tukhowsky equation? Or what? Or, do you know what this combination is?
Disappear in the eigenvalues.
Yeah, exactly. Okay, so we'll discuss it and we'll see why it's important. But for now, to avoid technical details, let me just say that it's a choice. So let's see how the phase space looks like, and you can all of these people that might be familiar with some condensed matter systems, that it looks very much like the phase space of solutions in quantum many-body systems that appear in the book of Subir, for example. So let me explain this, and then we'll break it down. So the first phase that we see is the so first of all, the phase space is
it's an isolated Kerr black hole. There's no
just Kerr black hole.
Okay, and the radiant, that's the gravity.
What's it?
Super radiant. That's the gravity waves coming out from it.
Well, I didn't even talk about gravity waves yet. It's just a single black hole.
Yes. Okay.
So super radiance is just the region where the wave is amplified.
Which way?
If you send a wave, you scatter away from the black hole. I would say a few words about how it is connected to gravitational waves, but the problem that I'm solving is black hole perturbation theory around a single black hole.
Okay, so this is the phase structure of wave scattering.
Yes. Okay, so the first phase is the super radiance phase. Again, here there's no news. This is all news. We can think about it as the analog of long-range order phase in quantum field theory and condensed matter. In those cases, it will describe ferromagnetism or superconductivity. By the way, here, zero here means extremality. Zero temperature is extremality, and this point here is when the angular momentum of the black hole is set to zero. So when we set the angular momentum to zero, we lose super radiance because there is no angular momentum. Okay, now at zero temperature, at extremality, the two phases, the super radiance phase and the standard phase, are separated by a point, which is very special. it occurs at this value of G that I will call GC, M over 2. Here, M again is the azimuthal number of the fluctuation. And the first thing that I'm going to show that at this point, there is a conformal symmetry developing. Somewhat, the symmetry will appear somewhat indirectly, and I will explain what I mean by that. But there is some hint of conformal symmetry at this point. And for that reason, I will call it a critical point. And that will be the analog of a quantum critical point.
So we have extremality. Is there an ADS2 type factor here? And you can just so everything can be written in 1+1 dimensions. Is that right?
Well, it's not just extremality. You also need to take the near horizon.
Yeah.
Yeah.
But is all of this happening in the near horizon region then?
No, I will not take any near horizon.
You won't. Okay.
Yeah. So of course there are many works on near horizon, extremal chaos. I'm going to show a different paradigm for symmetry enhancement.
Just for clarification.
Yeah.
It seems like you point out that 1/8 pi m when G equals 0, say that's 0 spin.
Yeah.
But how do I think about the y-axis here?
The working temperature. That's the working temperature.
With fixed A omega,
No, not with fixed A. With
fixed G, right?
with fixed G. Yeah, but this is just the working temperature. So I could write it for A if you want.
That
If you want,
point,
here A is equal to M and here A is equal to 0.
it's like an infinite frequency limit while A approach 0.
Yeah, if you keep G
The
fixed.
entire
Yes,
thing.
yeah, if you keep G fixed.
Okay.
Okay, so that's the first thing that I'm going to show, that the enhancement of symmetry at this point. However, the more remarkable thing is that even though at finite temperature, the symmetry is going to be broken, I'm going to show that there is a wide region in which the physics is controlled by critical fluctuations. And what it means is that in this region, the physics is described by a set of critical exponents. Okay, so the importance of this region, as emphasized in Subir's book, is twofold. One, that it is described by a set of critical exponents that provide what we would usually call a robust characterization of the system. But the second thing is that it extends to finite temperatures. So we have access to it. Finite temperatures means finite angular momentum. So we believe that in nature, most black holes have some angular momentum, and they are probably not too close to extremality, and they are probably not too close to 0. So the fact that it extends to a wide region with finite angular momentum is important for our ability to probe them. Okay, so that's going to be the general picture, and I'll stop to take some questions, but after that I will explain in this order.
So this is a qualitative picture, because I would have expected your critical region to hug that limiting line.
No, it's not.
It's not.
And we'll discuss it, but so the point is the following: the critical region, the boundaries of the critical regions are not sharp phase transitions.
Yeah.
They are called, again, in the book of Subir and in the condensed matter language, they are called crossovers. So there is no sharp distinction of when this region ends.
But it can be actually separated from this.
This line has a meaning, and I will explain where this line is coming from.
Yeah, okay.
I'll explain where this line is coming from.
And it is not the same as this black line.
It's not the same.
Okay.
And it's linear. So it's the picture is qualitative, but it does capture in this case, this line will be linear, and it follows from some scaling region, some scaling behavior around the critical point. So in different systems, the shape of the critical region will take different forms, and in this case, it will be linear. I will show that. Okay, let's start. So this is Tukolsky equation in full glory, and it's a little bit messy, but I just want to highlight a few important properties. The details here are not important, and complexity is not important, but two important things that I want to highlight. So it is separated into the angular and the radial equation, and it is solved by the method of separation of variables. So there is a separation constant appearing in the two equations. This is called the Starobinsky-Tukolsky separation constant. So the equations are really coupled in this way. We need to solve them both. And this separation constant is solved using the angular equation. It's an eigenvalue problem. And the eigenfunctions are called the spin-weighted spheroidal harmonics. And we can compute the separation constant. It's a function of this combination G. And this is what Prashant referred to earlier. So this equation depends only on this combination, A times omega, and this is the reason that I defined it in this way. So this property, of course, was known for many years, but it hasn't been used much, and it will play a crucial role in the story today. The radial equation, on the other hand, depends on both of the parameters. So here I define the dimension as temperature, so I simply rescale the working temperature with the mass. And the radial equation depends on both of these parameters, G and the temperature. So that's the technical equations that we have to solve. Let me redefine the separation constants, A. So I'll take this combination and I'll call it beta or beta squared. The reason is that it turns out that this is the combination that will appear in solutions, we'll see. But so from now on, I will call beta the separation constant. It's just a definition. And I will keep the subscripts here silent. So I will not put, so there should be subscripts S, L, and M on beta, but I will keep them silent. And a final remark is that, first of all, the separation constant can be complex. And moreover, because this is beta squared, so beta itself can also be complex even when A is real. So later on, I'll show some values of beta and keep in mind that they can be complex. So let's start, first of all, with the critical point itself, and I'm going to show a hint of conformal symmetry appearing there. So the critical point is at 0 temperature, and exactly when we tune the parameter G to the critical value, I will call the separation constant at this point beta C. And it turns out that at this special point, the radial Tukolsky equation simplifies considerably, and it reduces to the confluent hypergeometric equation. So that was discovered by Starobinsky and Tukolsky, and later by Tukolsky and Press long ago. So that's known. And this is important because this equation, we know essentially everything about it. So we can solve it. And this is the form of the solution, and depends on this parameter beta C. And a small improvement that I want to make over what's known in the literature is to say that to realize conformal symmetry at this point, because it's known that this hypergeometric function is an eigenfunction of the conformal symmetry group in one dimension. So let me make it more precise. At this point, the radial Tukolsky equation can be written in this form, where here I define some operator L0. And it turns out that this L0 is part of an SO 2,1 algebra defined here. So this is the algebra that I want to discuss. This is the algebra, but I can still, I can't claim that conformal symmetry is realized in this problem yet. Anyone can point out why? So the reason is that this L0 that appears in the equation is not Hermitian. There is a factor of I. And because of that, solutions to this equation do not realize the conformal symmetry. However, there is a way to realize the symmetry by analytically continuing some space-time coordinates. We can get rid of these factors of I in such a way that the operator is Hermitian and solutions sit in representations of this algebra. So I don't want to do that because I want to stay in the real world, Kerr in the real world, in Lorentzian symmetry, in Lorentzian signature. So I don't want to do that, but what I want to say is that it's an indirect realization of the symmetry. Indirect because we need to do some analytical continuation. If we do that, the symmetry actually can be shown to be exactly equivalent to the conformal ladder symmetry of the hydrogen atom. Okay, so this is why I call it an indirect realization of the symmetry. Strictly speaking, it doesn't appear for Kerr and Lorentzian signature, but it can be realized by analytical continuation.
So what are the operators in the hydrogen atom case?
What are they?
What are the operators that, what are
So what I claim is that this set of operators are essentially the same as in the hydrogen. They can be mapped.
Right.
This can be mapped to the hydrogen atom if we analytically continue.
so but in the hydrogen atom case, what do they physically mean, the operators? They're not the LX, LY, LZ, right?
No, they are not.
Because there's some conformal.
Right, exactly.
Okay.
So the hydrogen atom has tons of symmetry. In addition to the Runge length, there is
Right.
also a ladder symmetry that maps solutions.
I see. Okay.
Yeah.
So in this case, do you understand what this gamma 4 and D are? Like physically, do they mean anything?
Well, again, if we were to analytically continue, they would map solutions to the equations
Okay.
into each other
I see.
in such a way that solutions sit in representations of this group. Yeah.
So basically, your radial solution has a complex eigenvalue.
Yeah, that's
of
what-
this
yeah,
operator
yeah.
L0.
Yeah.
Well, for example.
Yeah.
Well, ordinarily, do people interpret L0 as something like an energy?
Yeah.
So does this
Yeah, but
work?
I don't want to do that because
Oh,
this
you
is
don't.
complex. Let's
I just wanted to see
yeah,
if there's some
yeah.
resonances or no, some decay, some other property.
But what I'm going to say now is that the following. So away from this point, the symmetry is broken anyway, and in any signature. But what we'll see that the symmetry breaking pattern will still constrain the physics. And this is why it's less important that the realization is indirect. Okay, let's see what I mean by that. So first of all, around the critical point, there is a scaling regime where tau is small, but we keep this combination fixed. That was, again, already discovered by Starobinsky and Tukolsky in the 70s. And I will call it a scaling regime to make the analogy with condensed matter more apparent. And in this regime, we can solve the equation in a perturbative fashion. So anyone that solves this kind of problems is familiar, might be familiar with the technique that is called a Mash asymptotic expansion. So in this region, we can solve exactly in separate regions. We can solve in the near horizon region and we can solve in the far region separately. And if tau, the temperature, is small enough, there will be an overlap between the two regions such that we construct a full solution. So boundary conditions are imposed on the horizon, measurements are done asymptotically, and we need a way to transfer the information about the boundary conditions to infinity. And if tau is small enough, we can match the two solutions and construct the two solutions and construct a full solution. Okay, so this is a classic result. Let me briefly sketch how it goes. In the near horizon region, the Tukolsky equation reduces to the hypergeometric function of this kind, 2f1, and we impose the ingoing boundary conditions. In the far region, it reduces to the confluent hypergeometric functions. There are two solutions with different coefficients, and the point of boundary conditions is to tell us or to set the ratio between them. And by doing the matching, this is exactly what's being done. The ratio between the two coefficients is fixed by the matching procedure. And this is the result. Again, this is a classic result. So I'm not going to derive it, but this is the result. In condensed matter language, this quantity is what we would call the susceptibility. It was discussed in the literature. For example, in this work, it was interpreted as the inverse of the Green's function of some dual field theory. And again, this is a classic result. We can see that this quantity that I call the susceptibility diverges with tau goes to 0 in this rate, with a rate that is determined by this coefficient beta c, which remember are nothing but the separation constants at the critical point. But because of this behavior, I will now call them critical exponents, because they control the way in which the susceptibility diverges at this point. Okay, any questions about that? So again, this is a review of results by Tarbinsky and Tukolsky. It's a very classic
Is this
result.
basically like a reflection?
Yeah,
You're sending an ingoing wave and you want to know how big the reflected wave is?
yeah, not exactly. I will show in a
Yeah.
second, but it's related to the reflection amplitude. Yeah.
Okay.
And I will discuss. I'll show the results for the amplitudes. So now there is something quite interesting about these results. It's not in the literature, but I think it wasn't emphasized. This form of the result is incredibly similar to some results in condensed matter. So this is the result for the susceptibility in the Ising chain in transverse field in 1+1 dimensions. And you can see the structure of the gamma functions is remarkably similar. So I haven't seen anything about that, but it points to some kind of universality of these systems. So those are some values for the critical exponents for different spins of the perturbations. Again, this kind, I put it in a language that is very suggestive to the problem. I call it critical exponents. But otherwise, these results so far are known in the literature, except for the symmetry argument. But the symmetry argument is not the main point I want to emphasize. So just to show that there are some values for the critical exponents of the system. It will become important because later I want to claim that we can, I'd like to suggest to try to measure them. So there are explicit values. And here, as Ramesh mentioned, the scattering amplitude is the observable that we might be interested in computing for the system. It is defined in the following way. So asymptotically, the wave function takes this form, where this is the incoming wave and this is the outgoing wave. The ratio between them is what's called the scattering amplitude. And in the scaling region, we have a solution, we can compute them. So they are related to this coefficient C plus and C minus, where here these extra coefficients are given by this formulation, by this formula. So they can be extracted from the solution. And the scattering amplitude, which is the relevant observable, can be computed. Okay, so so far again, this is mostly what's known in the literature. And now what I want to do is to push away from the critical point and see what are the consequences of the scaling behavior. So formally, we can construct the solution order by order in tau in the following way. So in the tau region, we have these two linearly independent solutions, and each one of them will receive corrections order by order in tau. Each one of these solutions have some asymptotic expansion with some coefficients. Now, typically, these coefficients will have to be computed numerically. Beyond the leading order that I showed, there is no analytical control over these coefficients, so they have to be computed numerically. And the amplitudes of the incoming and the outgoing waves will take this form in general. There will be a series corrections of the results order by order in tau. And in general, we can write them in this form. So the problem is really factorized into two parts. The first part is to compute this coefficient C plus minus, sometimes they are called the connection coefficients, and they carry the information about the boundary conditions at the horizon. And these functions, A plus minus and B plus minus that I defined formally in the previous slide, they are determined by the structure of the solution in the far region. Therefore, I will call them the kinematic functions of the far region. And the scattering amplitude can be written, at least formally, in this way. So again, this quantity here, which we can interpret as the susceptibility, carries the information about the boundary conditions. In particular, it contains the non-analytic piece from the horizon. And those functions here, which can be realized as a series expansion, can be computed mostly numerically, order by order in tau. And this is still very formal. And in particular, all of the quantities here will depend on the separation constant at every point on the phase space. Okay, so given a point on the phase space, characterized by tau and eta, there will be a different separation constant that will control, that will appear in the solution. So this is a continuum of functions. And in the next slide, I'm going to improve on that. And what I want to do is to try and extract some more useful, universal, and robust information from this. Instead of having the dependence of the scattering amplitude on the entire set of separation, continuum of separation constant, I want to extract something more robust. And the way to do it, before I do that, let me just emphasize. So for example, we saw that in the scaling region, these kinematical functions, they depend only on the critical exponents, beta C, okay? So the entire dependence on the set of separation, continuum set of separation constants reduces to the dependence on the critical exponents. And the claim now is that the following, we can now choose to look at the opposite limit in a way, the limit in which tau is kept fixed, but eta is taken to be very small. And what happens in this limit is that all these functions that appear in the scattering amplitude, the dependence on the separation constant reduces to dependence only on the critical exponents. And the reason is the following. In this, the separation constants depend on this coupling G. So whether we take tau to be small or eta to be small, in both cases, we'll get that the dependence will be only on the critical exponents. So I will mark this feature by lowercase c, and they can be computed from what I will call the reduced Tukhowsky equation. So this is the Tukhowsky equation in what we can now call the critical region. And the functional form of this equation may not look particularly simple. It's not much simpler than the full Tukhowsky equation. But the key point is that now the dependency on separation constants is only through the critical exponents and not on a continuum set of separation constants. That's a key point. So this equation is still solved numerically, or should be solved numerically, but we are guaranteed that in this approximation, the solution will depend only on the critical exponents, and the scattering amplitude, which is the relevant observable, will take this form. Where again, these kinematic functions can be computed either order by order in tau, or perhaps directly numerically from this equation. Okay, so that's the main point, and let me summarize it. So we see that in the phase space of solutions to the Tukowski equation, there is a critical region. And now these lines are explained. Okay, so these lines are exactly when eta is equal to plus and minus 1. And this is dictated by the scaling behavior. So it's a unique scaling behavior for the system that Tukowski and Starobinsky found. If we put in other powers, that will not work. It will either trivialize the equation or will be an ill-defined limit. So this is really crucial that this is the correct scaling behavior that we need to take, and it also determines the structure of the critical region. This is the reason that it's linear. In other systems, like in condensed matter, we have many different types of systems. The scaling behavior takes different forms with different powers in. This is, I believe, is similar to the Ising model in transverse field in 1+1, where these lines are also linear. And again, let me emphasize the importance of this. So in this region, the physics depends on a set of critical exponents. That's the first thing. And the second thing is that it extends to finite temperatures or finite angular momentum. So it's not, you don't have to be particularly close to extremality to probe this. So this is exactly the same kind of thing that is emphasized that Subir emphasizes in his book. That it's in a way, it's a way to probe the critical point at finite temperatures. Yeah, any questions about that? Yeah.
Maybe you're gonna come to this.
Yeah.
This is classical gravity that
Yeah.
you're solving,
Yeah.
so
Yeah.
there's no h bar anywhere or quantum, but I suppose once you express it in terms of the Hawking temperature, there is an h bar everywhere and looks very similar to quantum criticality. So you're really talking about a quantum critical point in some holographic quantum theory.
Well, okay, I have a few comments about that. First of all, I don't have any aspirations to say something quantum, or I'm solving the Tukowski equation. So to
Yes,
like
no,
to
I
wash
understand.
away any, I'm only solving the Tukowski equation. Now, whether how much do you want to take the word quantum seriously here? It's a little bit. Let me put it this way. The Tukowski equation is an equation for perturbation, for massless perturbations.
Yeah.
You can add mass, and then h bar will appear there explicitly with a mass. If you wanted to discuss, let's say, massive scalar perturbations.
Sure, I mean, that goes
Yeah.
back to the fact that h bar appears.
Yeah.
So no,
So,
I'm not questioning that.
Yeah.
I just wanted to
Yeah.
make sure my understanding was
Yeah.
correct.
Yeah. So, but
What we know from,
Yeah.
a lot of recent work, more recent work, is that when you have an ADS2,
Yeah.
there are quantum corrections, true quantum corrections that are, that can have very strong effects near extremality. And, this is what's come out from the SYK model and things like
Yeah.
that. So I'm curious are you suggesting that there will be further quantum effects that could perhaps be observable here?
perhaps, but I don't want to tie it to that because
Okay.
this is actually, I want to distinguish this from the near horizon extrema. This is not based on the isometries of the near horizon.
No, but
Okay.
it
So
must be that.
Everything is related. Everything
No,
is
let me relate
yeah.
the other exponent here, which is one, that is, this line is linear.
Yeah.
Could I have gotten that by just doing near horizon analysis?
Perhaps. I mean, again, everything is related, but the symmetry that I showed here is not the near horizon symmetry. That's the point that I want to make. Okay.
Okay.
It's not the same symmetry.
All right, but I mean, you're using these methods of Faulkner et al. That was all near horizon.
Yeah. Okay. I didn't say. Okay, you spotted out this paper, but well, they did it for ADS-CFT.
Sure.
It's just
sure.
the expansion. I just meant
I know,
the
but
technical.
everything they were doing was classical gravity,
Yeah,
but
yeah.
they simplified it.
Yeah.
The reason it's simplified is because near horizon.
Yeah. So yeah, everything is. I mean, at the end, it's a Kerr black hole, and it has all these properties. So everything is related. But the symmetry that I showed here is not the isometry group of the near horizon.
What is the symmetry? I'm sorry, maybe I missed that.
Yeah. So the symmetry.
What is the group?
So this is the symmetry. Again, as I mentioned, it's indirect. It appears only when we analytically
So which,
continue.
is it two different? Is it SL2R or?
Yeah, it's SL2R. So this is.
That is the isometry of the area.
Yeah, but it's not. No, it's not the same as SL2R.
Okay, different
It's
SL2R.
not the same group. It's not an isometry. This is not an isometry. It's a symmetry of the equation. Well, in an analytically continued spacetime, it's a symmetry of the equations of motion, but it's not an isometry. It's more like it's more like the ladder symmetry of the hydrogen atom.
Well, that's SO4, it's not SO4.
No, well, the SO4 includes the Runge length, but it also includes, well, it's actually not SO4. It's the ladder symmetry is not part of the SO4. It's in addition to the SO4.
Okay, I'm confused, but anyway.
But no, it's not an isometry. But that's not an isometry. This symmetry is not an isometry. It's a symmetry of the equation of motion. It's as if. I mean,
I don't know.
Is there an earthquake?
Yeah, it's
what's that?
You can't know what's
Stroke.
racing.
Ah.
Ground.
Shockwave. Binary American. Yeah. No, but I really want to emphasize it. This symmetry is not an isometry.
I know, but is it the same? Are these generated the same as the SL2 of ADS2 or different?
Yeah.
The SO2 alpha ADS2 is an
Maybe
isometry.
you're too focused on this.
Okay, yes.
Yeah, this is not an
So it's a
isometry.
different, completely different.
It's a different
algebra. All right,
symmetry.
fine.
Now everything is related because it's the same object, but it's not the same symmetry.
Okay.
Well, if you take like, for example, the Casimir operator of the isometry.
Yeah, this is the Casimir.
You probably get some form of differential operators. Right?
This is the Casimir is the critical exponent. Let me say now a word about, okay, so this is all very nice, and I computed the scattering amplitude. Now, what about experiment? If we had a black hole in the lab, we could just scatter a wave and measure the scattering amplitude, but we don't have it. So I want to say a word about how to connect it to experiment, and this is just really a word. I didn't develop it, but okay. So it's known by works here that are hidden, but work of Ivanov and Zhu. That the scattering amplitude measures tidal effects, okay, in black holes. And I will not show the details, but the intuition is that both of them are they are part of a linear response theory. The scattering amplitude and also the scattering amplitude really measures the
Cambridge Belton, it's unvetted. Whatever shook the ground, all of them, the whole area.
I'm on a site that says 0 earthquakes in the last 24
Yeah,
hours.
but there's, you know, on Reddit, people are saying, I felt it too, I felt it too.
Sorry.
Nobody's listening to your
Yeah.
talk. I'm sorry, I'm listening. I didn't feel it at all.
I didn't Yeah, so in any case, the scattering amplitude measures tidal effects, and tidal effects recently has been constrained by experiments. Here are two examples of papers. There are many authors on this paper, but it's Zaldariaga and some of his postdocs or former postdocs. And this is just to show that there are some constraints. Those are the tidal, those are parameters that parameterize the tidal effects, and there are some constraints. And this is another work by Chia, Zhu, and Ivanov. All of them were here and giving talks about similar topics. So this is just to say that there are current efforts to constrain tidal effects in black holes. And again, tidal effects are closely related to the scattering amplitude that I computed. So in principle, these critical exponents hopefully can be, we can hopefully try to measure them.
So you're saying that lambda 1 and lambda 2 for a given black hole are linked to chi for a given curved black hole for a given perturbation, etc.
Yeah.
I see. And this is analytically known as well.
Yeah, in this work. I mean, there are also, again, there are some caveats. I didn't fill all the details, but that's the general picture.
And this is the stuff that you can get from early in spiral as well, right? Even if you
this is early in spiral because tidal effects are important in the early phases.
And especially with emeries and stuff, you should be again be able to see some in the future. You'll be able to.
Yeah, so hopefully this will shrink, right? And we should be able to measure tidal effects. And So really the question, the point that I want to emphasize, okay, once we measure this, how do we extract from this a qualitative information about Kerr black holes? That's the point. And maybe let me say a word. You mentioned quasi-normal mode. So
Yeah.
what?
Does this have anything to do with the hidden symmetry story with this one too?
Good. It's better.
Okay.
So
I've been
I was
wanting to ask,
motivated by the
But
hidden
since you
symmetry.
said quasi-normal modes, I felt important.
Okay,
to ask.
how much time do I
Yeah.
have? Let's let me say a couple of words about quasi-normal modes and about the hidden symmetry. So when I asked so one could say that quasi-normal modes are robust prediction, and it's true that if you have the entire spectrum of quasi-normal modes, that's unique to the object. However, in practice, we don't measure the entire spectrum. We measure the first few modes, 3, 5, 7, and then it's up to you to decide if that's robust enough for you or not. If 3 is enough, 5 is enough, 10 is enough, I don't know. That's fine, that's good, but again, as I mentioned before, this is not what we would usually call a robust prediction in condensed matter, for example. So what I want to do is to extract from this something that is more robust, like the critical exponents. So if we can measure critical exponents, we can say Kerr belongs to some universality class. And if we measure this universality class, we can say with confidence that we've seen Kerr. If we just measure the first few quasi-normal modes, okay, it's up to your standards. Maybe for some people that's good enough, but that's not what we usually call strong prediction.
But with these critical exponents, you can only see them if the black holes in the merger are close to extremality, right? Like otherwise you would not.
No, that's the point. It doesn't have to be close to extremality. It extends away.
This is what I want to get
Yeah.
little better understanding.
Yeah.
So you got that little circle there, right?
Yes.
That's the extreme guy.
The whole line is it.
Yeah, the whole line is extreme.
Right, okay.
Yeah.
And then you're going off into finite
Yes.
tau,
Yes.
and then you got this eta,
Yes.
and you've got a theory which works for small eta,
Yes.
right?
Yeah.
Also small tau, or can you go to any tau?
Any tau.
So are you saying that if I went to, let us say, half the maximum temperature,
Yes.
I
Yeah.
can get precise predictions at
Yeah.
G equal to GC?
Yeah, exactly. So exactly above the critical point, the approximation is exact, becomes exact.
There is no quadratic term. How is it
No,
possible?
I mean, come on.
It's not-
Normally, it works for any eta, but you
Yeah.
have to have both G minus GC and tau small. But the ratio
Right.
can be arbitrary.
Oh, yeah.
Yeah, that's what I
That's
would have
usually
thought.
what it is.
Yeah. So that means that exactly above the critical point, eta
No,
is
but both tau
But
and G
tau.
minus GC have to be small
Yeah,
compared to some to GC, for example.
no,
But the ratio can be arbitrary. Eta can be anything. Too small.
no, the
quantity.
critical region is when tau is finite and eta is small.
Well, okay. That's right, that's the
Yeah.
quantum critical region I'm
Yes,
talking
yeah.
about. But there is some criticality, for all values of eta.
No,
Yeah.
that's a critical region.
Okay, so then you're putting G equals GC, okay, that's how
Yes.
that's fine.
Yes.
Eta is small.
Yes.
But tau also has to be.
No, it doesn't have to be
Okay,
small.
okay.
so you can really go up there,
I can go up. Now there is similar. So
and that's hard to believe.
Tau has to be big.
no, I mean this is look, when I set eta to 0, that will be exactly the equation. That will be exact when I set G to GC and keep tau. Here tau is finite.
Yeah, but this equation doesn't look scale invariant. You are making a small tau approximation.
No. Here there is no small tau.
Okay. or
It's not
maybe-
scale invariant. Yeah, you break the invariance group is only at this point. But here tau is not small. Now at I of tau, at some point that will break when we lose when there's no angular momentum anymore. This is also similar to condensed
Yeah,
matter.
okay,
It breaks at some point
Yeah, it does. Okay.
when we get to the microscopic lattice scale. But
Yeah.
otherwise, tau is finite.
Fine. I agree with that.
So what kinds of frequencies are we talking about? Like you had this A omega. So A omega has some region, right? Like within
Yeah.
this quantum critical region.
Yeah.
So what kinds of modes are we looking at for, say, low spin black holes?
Yeah, it's a good question. I didn't compute
Okay.
like the numbers.
Yeah.
We can try to look at this, but yeah.
Yeah, okay.
Maybe I should try to wrap up, right?
Yeah.
So let me just say a few words, and if people have questions, we continue. So just to complete this picture, so now there is we also have a symmetry breaking understanding of Kerr black holes. And let me just put it in context. So last year I talked here about my work with Alfredo about the self-dual configuration, which is mapped to the hydrogen atom. Now, this is not a realistic configuration. We can think about it as a toy model, but now it's put in, the emergent picture is really nice. So if the self-dual black hole is mapped to the hydrogen atom, now we see that we can think about Kerr black hole as quantum matter. And well, I cannot help by suggesting a very ambitious idea that in this sense, we can think about Kerr black hole as a composite object. If this carries on, of course, this is a very ambitious goal, but we might be able to develop this kind of understanding using scattering amplitudes. So treating this configuration as some fundamental configuration for which a full scattering amplitude for Kerr can be constructed. However, I'm mostly excited about or interested in the possibilities of measuring the critical exponents in experiments. So this is something I'm very excited about. And there are a few more directions that one can pursue, and I'm happy to talk to people about it. But let me end it.
If you have questions on Zoom, please raise your hand and I'll call on you.
Okay. So I was just wondering, in the Iconal limit, what do these critical exponents correspond to? Like,
yeah, it's a good question. I didn't look at it. I want to, yeah, so I connected it to the tidal effects, but I also want to, yeah, to connect it to photon ring and stuff like that.
Yeah, because like exponential, you're showing that there's some like some divergence of your reflectivity,
Yes.
right?
Yeah.
In the Iconal limit, you will get something similar as well. But what does
Yeah.
that mean in the photon ring picture? It would be, I think, interesting.
Yeah, very much so. Yeah, that's one thing I want to see the effects of photon ring. And also on tidal effects, because I showed just the general picture, but the details have to be filled in. But yeah, very much so also for the photon ring. Yeah.
Let's go to that picture.
Which
The cone. Yeah, this one. So as I go off from tau equal to 0,
Mhm.
is this cone likely to tilt?
No,
There must be a tau squared, something.
no.
Correction,
No.
nothing.
No. No, so look, the claim is simple. Take the Cauchy equation,
Yeah.
put eta to 0, tau keep fixed, you get this. And that depends only on the critical exponents. That's the claim.
Yeah, but there is a tau appearing in the equation. Doesn't it
Yeah.
have any effect?
It appears that, yeah, it's part of the solution, but it can be finite. The point is not so much tau. The point is that the dependency is only on the critical exponents.
No, but I think Ramesh's point is also that when you set eta equal to 0,
Yes.
as you go G going to GC,
Yes.
your tau is also going to 0, right?
No.
No.
Yeah, I mean, it's not tau C. Okay. Because tau
No,
is a
there's no
temperature.
tau C.
No, but tau is a
You have two parameters, either tau and G or tau and eta. I can parameterize with tau and eta. And I can control them separately. I can set eta to 0 and keep tau finite.
No, but I thought tau was a dimensionless temperature.
Yes.
So at the critical point where you have A going to 1, you have G going to GC and tau going to tau C as well, right?
No, there is no tau C.
Tau goes to 0.
No, it
Yeah.
doesn't go to 0.
You mean along this curve? Yeah, right.
I can choose to take eta to be 0 while taking tau fixed.
Right, I agree. But I'm saying the critical point is that tau equal to 0.
Yeah, critical point is
So it's
tau.
the double limit. You're saying now when you go off into that the quantum physical
It's a
region,
different limit.
Okay.
It's a different, so there was one limit that I consider, which is called the scaling region. This is when tau is small and eta is kept fixed. This is this cap. And this is the opposite limit in a sense, where tau is finite and eta is taken to be small.
Let's do last question.
Is the blue region exactly tangent to the red one, or is that just a cartoon?
Is it exactly tangent to
Is
what?
is the boundary of the region tangent to the red one, or is it just the cartoon?
Yes, in the sense, it's exactly tangent in the sense that this is linear. But as I mentioned before, this is not a sharp phase transition. It's a crossover. They call it crossover in condensed matter. So it's essentially an approximation. If you are exactly above the critical point, the approximation is exact. And the farthest, and as you go away from this line, the approximation becomes worse and worse. So this is just yeah, it's not a sharp phase transition.
But is there a quantum critical region that overlaps with the superradiance? Is that possible?
Well, if your standards
wondering whether this
are low,
boundary-
it will overlap. Yeah.
This boundary, I think, has to be, that's where
This is a
tau
sharp.
square.
This is sharp.
This is sharp,
So
of course,
yes.
completely well
And
defined.
this is not sharp. It's just to say that the approximation scheme is when eta is with respect to eta of order 1.
Can I ask,
Yeah.
a naive question, which is, everything that you said seems classical, right?
I think
Isn't it?
what you
But so
do
in what
is
sense is it a
you
quantum
do-
critical?
Yeah, exactly. So that's also I don't have any aspiration.
Oh,
So
in fact.
I'm solving the positive
Yeah.
equation.
I have a
So
feeling
you
even
can
this
consider it semi-classical.
vertical line is probably.
It's massless, so there is no
This
H bar. But
whole
if you had mass, you would
core
see H
must
bar more
be-
explicitly. So
Yeah.
perhaps you can call it semi-classical.
But
But I'm just solving this
because
positive equation.
for arbitrary
Whether you want to call it classical
So
or
in the last slide, you're saying arbitrary
Is the
scheme is
quantum
like-
critical point just
just
a
for-
name for a critical point?
Yeah,
Yeah,
critical
yeah,
point.
right.
I just
At
wanted to
zero
make the
time.
analogy
But there was a tau there.
with condensed matter. It's a critical point.
No, arbitrary.
Well,
So
then if it is a
any
critical
point-
point, there should be questions like
eta equal to
what
zero.
Yeah.
universality
Any
class
that line,
does a
if you solve
photon
the
to?
This is the
first equation, essentially
the
make it
universality class is
for that
characterized by
entire
these
line.
critical exponents.
Yeah.
And
But there are those words like that
I
has,
think maybe.
I only have heard those words, but there are those words, studying quantum fluctuations, including those, they have those Schwarzian theories of horizon, near external black.
that's okay. That part is-
Do they have-
finite spin.
Yeah, that's what
Okay.
Superior asked. I mean, I don't have something concrete to say about
Anyway,
it.
this is very
Okay,
good.
okay.
It's all related because it's all Kerr, but it's a
Good
different type
start.
of symmetry. Yeah, absolutely. Yeah.
Yeah. That was great.
Thank
That was
you.
great, yeah.